this example is not only the difference between 3NF and BCNF, also we will perform a complete recap of the entire session. So here the question is, find the appropriate normal form. Whenever the relation is given as R, A, B, C, D and E, and the set of functional dependencies given BC to D, AC to BE and B to E. Now I will tell you the query that many students asked me in the previous class, that is why you are considering each and every time that the relation is already is in 1NF. Why you are not checking it? So now I will tell you the not the trick, the actual rule how we could find a particular relation is in which normal form. So I don't know R is in which normal form. So what is the starting point? So the first step is, as we know that we have to find out the candidate key from the age diagram. So I can draw the age diagram or I can find it from the RHS. So in the RHS, A is absent and which one is absent? C is absent, right? So here the first point is clear. A and C, they are the essential attributes. So I will try to find out the closure of AC. So from AC I am getting AC. From AC I am getting BE. From B I am getting E. It is already included. From BC I am getting D. So I am including D. So it is proven that AC is the candidate key. So we have identified the candidate key, but here try to understand. After finding the candidate key, if you find that your candidate key is a combination of more than one attribute, then you have to check one more thing. What is that? You have to prove that the subsets individually A and C, they are not a key. Means from A I am getting A, from C I am getting C, and from A I am not getting anything luckily, and from C I am not getting anything. So whenever your candidate key is a combination of more than one attribute, then just check whether individually they are key or not. If they are individually key, then it is not a candidate key, because candidate key must be minimal, means no subset should be a key. So in this case, A and C, the subset of this candidate key are not a key. So that's why it is a minimal one, and we can say that it is a candidate key. So it is proven that AC is the candidate key for this relation R. Now I will tell you the answer. So now we have to check whether it is in 1NF or not. Now I will tell you one trick, and this question is repeatedly asked. Whenever I started this class, I have clearly explained that we are not dealing with database management system. We are dealing with relational database management system, RDBMS. So what is the difference between DBMS and RDBMS? RDBMS means whichever information or whichever data we are keeping, means the collection of data is kept inside the schema, means we are using a table format where we have columns as an attribute and tuples as a row. So whenever we are storing our data in terms of a table or schema, then this kind of thing is known as, or this kind of repository is known as relational database management system. Now I will tell you that why each and every time I am assuming that our schema is in 1NF without checking anything, because RDBMS does not allow multi-valued or composite attributes. So whenever I am talking about RDBMS, there is no chance that a particular column is having more than one value. So you have to consider this, each and every column is having only one single value, that is the atomic value. So this is a rule of RDBMS. So that's why always the RDBMS will be in 1NF. So no need to check. So now we have to check whether this relation is in 2NF or not. So how we can check? So let's take the functional dependencies one by one. But we know that to prove partial dependency, in order to prove that relation is in 2NF or not, we have to find out prime attribute and non-prime attribute. So here, which one is the prime attribute? We know that whenever we have the candidate key, the subpart of the candidate key or subset of the candidate key are the prime attribute. So in this case, this is one part of the candidate key and this is another part of the candidate key. So here we have two prime attribute, A and C. And which one is your non-prime attribute? A and C is included as prime attribute. So rest of the attributes are considered as non-prime attributes. So B, D and E. So after making this list, now we will check whether this relation is in 2NF or not. So now how can we check? So first I will take this first functional dependency, BC to D. So how we can check? See, this one is in 2NF because BC is not a proper subset of candidate key. So AC is the candidate key, BC is not a proper subset of this candidate key. So we can say that this is not a prime attribute and it is non-prime attribute. So the definition of partial dependency was whenever a prime attribute is finding any non-prime attribute. So in this case, BC is not definitely a part of this candidate key. No. So in this case, it is not partial dependency. So fine, it is in 2NF. Now let's check the second functional dependency, AC to BE. There is nothing to check. It is already in 2NF because AC itself is the candidate key and candidate key can find other non-prime attributes. So it is fine. Then the third relation, that is B tends to E. So from B, I am finding E. So in this case, here we can say that it is also fine because B is not a proper subset of AC, candidate key. So this relation is also fine. So in this case, I can say that the relation R is in 2NF. So it is definitely is in 2NF. Now the third checking, whether this relation R is in 3NF or not. So in case of 3NF, what we will check? Whether the left hand side of the functional dependencies are super keys or not. Now I will tell you the actual definition of the 3NF case 2. Here the rule is, the first rule is fine. That is, LHS of the functional dependencies should be a super key. All the LHS. And RHS should be a prime attribute. This is the next condition. And RHS should be a prime attribute. This is the actual definition of 3NF. So what is the meaning? I have explained that the definition of the partial dependency is prime to non-prime. Definition of transitive dependency is non-prime to non-prime. So if you check the RHS part, you will always get non-prime thing. So partial dependency and transitive dependency both are bad thing. So to be in 3NF, if your RHS is prime, then also it is in 3NF, or else the LHS of the functional dependency should be a super key. So please make a note. However, in case of BCNF, the only condition is whichever functional dependency is given to you, left hand side of the all the functional dependency should be a super key. So this is the definition. There is no checking of RHS part for BCNF. However, there is a checking part in the RHS in 3NF. To be in 3NF, either this one holds true or RHS should be a prime attribute. So now let's check whether this relation R is in 3NF or not. So here if you consider the first functional dependency BC to D, so in this case neither BC is a super key nor D is a prime attribute, because D is not here as a prime attribute, or BC is not a key. Here AC is the key. So this condition fails. So both the condition fails. Again check for this one. This one I am not checking because for this one, this is the key. So it is satisfying the property of the 3NF. But here the rule is each and every functional dependency should satisfy the property. Now for B tends to E, again the problem, neither B is the super key nor E is the prime attribute. E is not here in the list of the prime attribute and B is not the super key. Here AC is the key. So these two conditions are not satisfying the rules for 3NF. So I can say that this relation R is not in 3NF. So if the relation R is not in 3NF, then there is nothing to move forward. Then it is not in BCNF also, because to be in BCNF, the first rule is the relation must be in 3NF and all the LHS of the given functional dependencies must be a super key. So this condition does not satisfy, so it is not in BCNF. So here my question is, what is the highest normal form of this relation R? The answer is 2NF. So this relation R is in 2NF, right? Now, if I tell you this question, what is the difference between 3NF and BCNF? So you have to answer it like this. For 3NF checking, we have two conditions to check. And here you can ask me one question, that is this checking is in or and, means we have to check both or any one of them. So it is either, right? So here my point is, to prove some relation to be in 3NF or not, either you check LHS part, which is a super key or not, all the LHS of the functional dependencies, or you can check that RHS of the functional dependencies are prime attribute or not, right? It is either or. But for BCNF, there is nothing to prove. First thing, you have to take the LHS of all the functional dependencies and you have to prove that whether they are super key or not. And don't get confused. Whenever something is proven to be a candidate key, it is definitely a super key. So that's why I am not checking them as a super key. Each time I am going to find whether they are candidate key or not. So since candidate key is a subset of super key, so it is easily we can prove that it is also a super key. So that's why my first step is I'm drawing the edge diagram and finding whether the LHS are candidate key or not. Now I will give you one more example. That is, if there exists any situation which is not a BCNF, not in which situation we have not a BCNF situation. Say I have one table person. So we have some S number, name, address and hobby. So in this case, some functional dependencies are given. So here only one functional dependency is given. From S number, I can search for name as well as address. So in this case, the question is, this person table is in BCNF or not? This is the question. So what we can do, the only thing we have to check is whether the left hand side of the functional dependency is a super key or not. My answer is no, because from S number I can get S number, I can get name and I can get address only. But to be a key, all the attributes must be reachable. But from S number, I will not be able to reach this attribute. So at this point of time, I can prove that this S number is not a key, means not a super key. So in this case, if this condition fails, I can directly state that it is not in BCNF. But there is again one question. So, in which normal form it is? Is it in 3NF? So again I have to check. But this kind of checking is required at this point of time, because in 3NF also we know that if a functional dependency is given, then LHS must be a key, right? This is your condition number 1 for case number 2. So in this case also this relation is not in 3NF also. So now can we check for 2NF? So is it in 2NF? How we can prove that? We have to prove partial dependency exists or not. How to check partial dependency? From the key attribute, if the subset of the key attribute can find any non-prime attribute. So which one is the key? So from S number up to this it is reachable. So how to reach this attribute? So I have to make a key like this, S number and hobby together. So if I take S number and hobby together as a key, so from S number hobby I will get S number hobby. And from S number, name and address is reachable. So in this case, which one is the key? S number and hobby together is a key. So which one is the prime attribute? Any subpart. So here from any subpart, I will be able to reach any non-prime attribute or not. So these are the prime attributes. So we have S number and hobby as a prime attribute. And which one is the non-prime attribute? That is the name and the address. So is there exist any relation that from S number I am getting name or from S number I am getting address? It is happening, right? So there exists partial dependency. So it is not in 2NF also. Now there is one question. So 1NF I am not checking, because if I am talking about RDBMS, it is in 1NF. But now the question is it a candidate key? What is the definition of a candidate key? See, according to my discussion, it is a super key. And candidate key is, if it is minimal in nature, then I can say that it is a candidate key. How can I prove that it is minimal in nature? Simple. Not S number alone is a key. Not hobby alone is a key. So the combination of S number and hobby is minimal. So it is a super key as well as it is a candidate key. So got my point? So this relation person is not in BCNF, not in 3NF, not in 2NF. So what is the highest normal form? So this is the trick. Now you have to remember that logic, that RDBMS by default is in 1NF. So the highest normal form in this case is 1NF.